Hello. 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 Shumon, please tell me now. Am I audible now? Shumon, please tell me. Am I audible? Hello. Hello. I think yes, yes. Okay, thank you. So actually, I before going to discuss fitting of binomial distribution, I uh, discuss some notations or some definitions. That is, for first I consider trials. The trials means an attempt to produce a particular event which is neither certain nor impossible. For example, throwing a die to get a 6 is a trial, another throwing a coin to get a head is a another example of trial. When a trials are repeated, they form a series of trials. Trials are said to be independent in relation to an event if the probability of event in any trial is not affected by the supplementary information about the results of any number of other trials. A series of trials are said to be Barnolian series of trial if the possible results of any trial can be divided into two classes, which we conveniently call success and failure. Secondly, the trials are independent. And thirdly, the probability of success or that of failure remains constant from trial to trial. For example, suppose n throws of a fair die, may be looked upon as a set of Bernoulli trials. This is the example of a Bernoulli trials because we use same die, so probability of success and probability of failure, that is remain constant, and it is a half because we use fair die, and each throws are the trials are independent, and each throw of a die, if I consider the appearances of 6 on the uppermost face, if I define success as a appearances of 6 of a 6 on uppermost surface, then we see that there are two possibilities in each trial, that is either success, that is either 6 is appeared or not, that is failure. And sorry, and since it is a fair die, so the probability of success should be 1 by 6, that is probability of getting 6. Okay, so the in previously I mentioned that is how it is wrong, please, sorry for that. Okay, so probability of getting 6, that is 1 by 6 because I use a fair die, and that is probability of success. Similarly, probability of failure, that is 1 minus 1 by 6, that is 5 by 6. Okay, so these are fixed for each trial. So it is a example of a Bernoulli trial. So in throws of fair dice, the example of a Bernoulli trial. Another example when in throws of a fair coin, and I define success as a for getting head. Okay, so here we see that probability of success is half and failure is also half, and this is constant for each trial, and each trial has a two outcome, that is success and failure. So this is a another example of a Bernoulli trials. So suppose we have a n series of a Bernoulli trials, or Bernoullian trials, and x defined as a number of success, then the random variable x follows binomial distribution with parameters n is a number of trials, and p, which is success probability. And the PMF of x is ncx p to the power x 1 minus p whole to the power n minus x. Okay, so we know this thing. So now for fitting, the we proceed as follows. First, if you have suppose your p is unknown, so first step is we need to estimate p. And how? Since we know expectation of x is equal to, which is mean of x, is np. So using method of movement, and p is p unknown and n is known. Okay, I denote this estimated value by of p by hat. So np hat is nothing but a x bar. X bar is a sample mean. So therefore, hat p is equal to x bar by n, and then replace. So now with p hat in place of p, we proceed as follows. So step 2, so we compute this ratio compute this ratio. Sorry. Since p is unknown, so we replace p by p hat. Sorry. This is x, not x minus 1. So please change this thing. 1 minus p hat n minus x. So this is n factorial x plus 1 factorial n minus x minus 1 factorial n factorial x factorial n minus x factorial p hat x plus 1 1 minus p hat n minus x minus 1 p hat x 1 minus p hat n minus x. So this is nothing but a this cancel out. So n minus x plus 1 into p hat 1 minus p hat, sorry, this is p hat 1 minus p hat. Similarly, px by px minus 1, this should be n minus x plus 1 by x plus 1 by x into p hat 1 minus p hat. Okay. So p hat, I think it is better to denote, since p is unknown, so we replace p by p hat. So this should be p hat x plus 1 instead of p. So this is the estimated probability. So p hat x equal to capital X is equal to small x is nothing but a n minus x plus 1 by x into p hat by 1 minus p hat into p hat x equal to small x minus 1. Where, since if you see that the PMF of x, which is this, the range should be 0, 1 to up to n and equal to 0 otherwise. So here x should be 1 to up to n, because if you take x is equal to 0, then p hat x is equal to minus 1, this is 0. So it is meaningless. That's why this equation is valid when x is equal to 1 to the root small n. So what about p hat x is equal to naught? So this is nothing but a 1 minus p hat whole to the power n. So first we compute this part. First we compute this part. Then for p hat x is equal to 1, we use equation 1. According to the relation, if x is equal to 1, then this is n by 1 into p hat by 1 minus p hat x is equal to 0. So this is n p hat 1 minus p hat by into p into 1 minus p hat whole to the power n. Similarly, p hat x is equal to 2. This is n plus 1 by 2 into p hat by 1 minus p hat x is equal to 1, and so on. In that way, we compute all probabilities for x is equal to 0 to n. Then step 2, now in step 3, the expected frequency of x success, which is equal to n into p hat capital X is equal to small x. And note that if your p is known, Then proceed all the steps. Then proceed all the steps except you use p hat. We use p. Okay. So step one is not needed, is not required because p is known. But in step two, p equal to small x by px equal to small x minus 1, which is equal to n minus x plus 1 by x into p by 1 minus p. Okay. So using this relation, we compute p equal to x, which is nothing but n x plus 1 by x, p into 1 minus p, p x is equal to small x minus 1, for x is equal to 1 to up to n, and for x is equal to 0, we use this formula 1 minus p whole to the power n. When p is known, and the expected frequency when p is known, the expected frequency when p is known for x successes equal to n into capital P into cap p equal to x is equal to small x, where n is a total frequency. Okay. So now I consider an example. A survey of 320 families with 5 children each revealed the following distribution. That is, number of boys, the family, 0 is there is no boys. How many families are there? So this is the frequency, the number of families. This is the frequency. There are 12 families who have no boys. There are 40 families who have one boys. There are 88 such family who have two boys. There are 110 such family which have three boys. There are 56 such family who have four boys, and 5 such family there are 14 such family there are 5 boys. Okay. So if you if I ask you fit the appropriate distributions, then first you see that first you need to define the random variable, that is x, that is the number of boys. in a family. So here we see that the maximum number of boys, that is the in a family, that should be 5. Okay. Then you see that each family, that is each cases, under each family, each cases or each children, either it is a boys or boy or girl. Okay. There are two possibilities for each family. There are two possibility, one boy, either boy or girl. Okay. So first we define the random variable. Before fitting the distribution, I ask you fit the appropriate distribution. First you define the random variable. The random variable is number of boys in a family. Okay. So then in each family, how many children are there? 5 children. So here the number of trials should be 5. So this survey, we consider 320 families, which each family has 5 children. So, and this is the distributions of a 5 children. This is observed frequency. So number of boys in a family, maximum number is 5 and minimum number is 0. And each children under each family, either boy or girl. So there are two possibilities, success and failure. And probability of success for each children is fixed. You can assume that. So similarly, probability of girls also, that is failure, also fixed, since there are two outcome. Next thing, the trials, that means 5 children. Here the trials are uh, here the 5 trials. Okay. And each trials, and these 5 trials are independent, because if the first issue whatever the boys and girl, it does not depend on the second children, whether it is boys and girl. So the all 5 trials are independent. So here we see that one, 5 trials are independent. Probability of, there are two possibility, each each trial, that is either boys or girl, that is success and failure. And probability of success is constant, that is probability of boy is constant. Similarly, probability of girl also constant. So it is a example of a Bernoulli trials. So it is a 5 Bernoulli trials, and according 5 Bernoulli trials. Okay. So here the random variable is a sum of 5 Bernoulli trials. This is for first children, this is for second children, this is third, this is fourth, and this is fifth. So we can assume x follows binomial 5 comma p, where p equal to probability of boy. But here p is unknown. So you need to estimate P based on this observed frequency table. So in step 1, we need to estimate P, and we know this P hat, I already mentioned this in my previous discussion. That is, when P is unknown, we estimate P hat by x bar by n, where x bar is a sample mean. So here P hat equal to x bar by n is 5. Okay, and x bar is a sample mean which is equal to sum over xi fi by sum over fi, and here total frequency is 320, and this is the xi and this is fi. So therefore we get summation xi fi is 840 according to my calculation. Please take this thing, and hence x bar is 2.625. Therefore 2.625 divided by 5, then p hat equal to 0.525 approximately. Please check this calculation. Okay, so now in step 2, probability x is equal to 0, which is equal to 1 minus 0.525 whole to the power 5. Why? If you look at the PMF of x, which is equal to in 5cx p to the power x 1 minus p to the power n 5 minus x, where x is equal to 0 to 5, equal to 0 otherwise. So therefore p x is equal to 0 is 1 minus p whole to the power 5. Since p is unknown, so it should be 1 minus p hat whole to the power 5, which is equal to this, and I got this value is 0.02418. Please check. Now compute this part. X n plus n. Yes, Shuman, I also thank you. I also get this value 2.625. Please calculate remaining part also and help me whether I'm there is a error or not. Okay, please, if there is error, please tell me, and please calculate quickly. Okay, so x, this is the first column. The second column, n minus x plus 1 by x into p hat by 1 minus p hat. So this is equal to Since here n is 5, so it is 6 minus x by x into p hat 1 minus p hat. Okay. Okay, thank you, Shayuk. Thank you. So 0, 1, 2, 3, 4, 5. I approximate this value. Okay. Uh, what do you mean by Shuman? Okay, 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 okay. I thank you, thank you. So the first column is this, that is the realization of capital X. I do not compute the first entry of second column because x is equal to 0. For x is equal to 1, it should be 5.52630. Okay. Then for third entry for second column is 2.21052. Fourth entry 1.10526. Fourth entry 0.55263. Okay. So, and when it is 5, that is 1 by 5, please tell me the last portion, that is 1 by 5. P hat is 0.525. 1 minus 0.525. Please tell me quickly what is the value of this. Sumon, Shayok, please tell me. Please tell me this value. Third column. Please tell me this value. And third column, that is P hat x is equal to small x, which is equal to n minus x plus 1 x p hat. That means the second column into p hat x minus 1. Okay. So it is 0 0. I take Shayok answer because here I consider 5 decimal places. Okay. Thank you, Shayok. 0.2210. So that is, we can write instead of n minus x plus 1 by x p hat 1 minus 1 x, column 2. I think it is better to write second column instead of second column. I think it is better to write column 2. Column 2. And this one is column 1. Okay. This is column 3. So, okay, thank you, Shuman. So, column 2 into p hat x minus 1. So, for first entry of column 3, this is, I just put this value 0.02418. Now, just see that, multiply this with this, then I get this value. just look at the arrow, multiplied this with this, and I get this value, which is equal to 0.1332. Similarly, multiplying this with this value, I get this value, which is 0.29537. Again, multiplied this value with this, so I get this value, that is 0.32646. Similarly, this is 0.18041. Multiplied this, I get this value, 0.03996. Okay, so again I repeat this thing once more. First I compute directly this value, then use this value, I multiplied this term and this term, and this term, multiplied these two terms, I get this value. Similarly, multiplying this and this value, I get this value. Similarly, I multiplying this and this value, I get this value. Similarly, multiplying this and this value, I get this value. Again, multiplying this and this value, I get this value. Okay. Now the last column, that is column 4, which is expected frequency. Expected frequency is nothing but a capital N into p hat capital X is equal to small x. Here capital N is 320 into p hat x is nothing but a, which is in column 3. So just write into column 3. So we get first entry is 7.74. Because the frequency is a integer, so we approximate rounding this to an integer, which is approximately 8. Okay, Shayok, if you look at the formula, Shayok asking me why this is happening. Okay, just look at this formula. This formula. Look at this formula. I already deduced this thing. Again, I repeat this here also. Just see carefully. I take a ratio of this. So this is in generally I write this in Cx p hat whole to the power x. Because p is unknown, I replace p by p hat n minus x in Cx minus 1 p hat x minus 1 1 minus p hat n minus x plus 1. So this is n factorial x factorial n minus x factorial and p hat n factorial x minus 1 factorial n minus x plus 1 factorial. Okay, so it is 1 minus p hat and after simplification it is this. So therefore p hat x equal to small x is equal to n minus x minus n minus x plus 1, sorry, it should be plus 1 instead of minus 1. So it is by x into p hat by 1 minus p hat into p hat x is equal to small x minus 1. Clear, Shayok? Clear? It's clear, Shayok? I use this formula, and so x should be 1 to up to n instead of 0, because when x is equal to 0, p hat x is equal to 0 is 0, hence it is not defined. So that's why I use this formula for x is equal to 1 to n, and for x is equal to 0 I compute directly, that is 1 minus p hat whole to the power n. I okay. First line why I compute this directly, okay. First entry of column 3 I compute, just use this formula. Why? Because this formula cannot work. This formula cannot work for x is equal to 0. But we want x is equal to 0 for use this formula. So for x is equal to 0, I compute directly. That means p hat x is equal to 0 is 1 minus p hat whole to the power n. Here n is 5 and p hat is 0.525 whole to the power 5. Okay. Okay. Thank you, Shahrukh. Thank you. Okay. So in that way we compute column 3. Now for column 4, it is 42.76, which is approximately 43, and third entry is just multiplied by n, that is 320 with column 3, then I get this thing, which is approximately 94. Okay, you can consider 94 or 95, but you should think about the total frequency should be 320. Okay, 46 approximately 104, 57.73 approximately 58, 12.79, which is approximately 13. Because why I use, one thing I want to tell you, instead of 105 I use here floor function, that is the I take a integer which is less than 104.46. Okay, so that is called floor function, that is 104. Why? Because if I take 105, then if you add all this frequency, 8 plus 43 plus 94, 105 plus 58, 13, this gives 321, which is not 320, but it should be 320. So that's why we need, that's why we so it is okay, sorry, this is my mistake, it is okay. 420, I want to point it out, this thing 94, instead of 95 I write 94, because if you look at the portions, here I use instead of 7.74 rounded 8, so here something is extra. Similarly here also something is extra. Okay, and here something is subtracted, that is 0.46 is less. Similarly here something is extra, here also something is extra. Okay, so as a whole it should be 320. So if you add all this value, if you rounded this 94.5 to 95, then you see that the sum should be 321. So somehow where you should cons- uh, you should uh, negotiate this one where it is possible, only there, because this is if you consider 94 or 94, this is, it is not a great loss, okay, because 94.52 is close to 94, even and also 94.52 also close to 95. The error here, the error is very small, that is 0.02. Okay, so that is why, okay Shag, I am telling you after explaining this part. So that is why i I use here floor function instead of ceiling function. Okay, so if you add all this thing, then it should be 320. Total is 320. Okay, Shayo, you have written x is equal to eto instead of eto. Where, Shayo? Oh, sorry. Okay, thank you. Thank you, Shayo. I need to correctly identify this point. This should be x minus 1. Okay, so this is okay. Thank you. So now in column 5, I write the observed frequency, that is 12, 40, 88, 110, 56, 40. So now if I compare observed and expected frequency, we see that they are very close to each other. Hence, we can conclude that fitting is good. And you also you can draw multiple bar diagram, that is one for expected frequency and another for observed frequency. Here it is look like this: blue color for observed frequency and red color for expected frequency. So I use, okay. This is the roughly draw this picture. So you can use your graph paper and draw this thing. Okay. For illustration purpose, I just roughly draw this thing. Okay. So blue line for observed frequency, So this is a multiple bar diagram. Okay. So in a way, we can see it visually that the fitting is good. Okay. So just I recap all the steps one by one. First, I define the trials. Actually, trials means the attempt to produce the particular events. Then I consider the repeated trial. Then I define independent trials. Then I define Bernoulli trials. Under n Bernoulli trials, sum of n Bernoulli trials give a binomial distributions. This is the PMF of binomial distribution. Some of example of Bernoulli trials is when a when we throw a die in throws of a die. This is an example of a Bernoulli distribution. In throws of a fair coin. This is also another example of a Bernoulli distribution. These are the steps. If P is known, then I just go to the step 2. That is this Px is equal to small x by Px equal to small x minus 1, and which is equal to n minus x plus 1 by x into P by 1 minus P. That is, in that case, we do not need to estimate P. Okay, and proceed the same way. Uh, that is step 2 and step 3. And when P is unknown, we need to estimate this. That is, we estimate P hat by x bar by n, where n is a number of trials and x bar is a sample mean. And the steps are as follows. First, I compute directly P hat x is equal to small x hat P hat x is equal to 0, that is 1 minus p hat whole to the power n, and when p is known, that is just 1 minus p whole to the power n. Then compute n minus x plus 1 by x into p hat 1 minus p hat when p hat is unknown, and when p is known, I just compute n minus x plus 1 by x into p by 1 minus p. Then using p hat x is equal to 0 when p is unknown, we compute p hat x is equal to 1. Again, using p hat x is equal to 1, we compute p hat x is equal to 2, and so on. When p is known, we compute using p x is equal to 0, we compute p equal to x is equal to 1. When using p equal to x is equal to 1, we compute p x is equal to 2. And for expected frequency, that is n into p x is equal to small x when p is known, where capital N is a number of total frequency. Okay, capital N is a total frequency. So when p is unknown, the expected frequency is n into p hat x is equal to small x. Okay, so in that way, then we compute expected frequency, both cases when p is known and p is unknown, and compare the observed frequency. And it is best practice is, if you draw multiple bar diagram, one bar for expected frequency, another bar for column, uh, another bar for observed frequency, and if these two bars are very close to each other, that means your fitting is good. One point you should notate, that is the if uh, for one for fitting of a binomial distribution, n should be not very large, it should be less than 30. So number of trials should be less than 30, and p is not very small, or p hat not very small. So if n is less than 30 and p is not very small, then we use Bernoulli trials, and we use binomial distribution. One more thing, for fitting a binomial distribution, if you have no idea about the data, if suppose your n is large, suppose n is around 25, p is you do not know p. In that case, you first compute mean. Okay, so np is a mean. First you compute mean, that is the sample mean. That is sample mean. First you compute sample mean and sample variance. For frequency type data, this should be xi into fi by capital N, I denote this by x bar, and sample variance, I denote this by small s square, which is equal to n minus 1 sum over 1 to k. Suppose there are k categories, xi square fi minus capital N into x bar square. If you see that x bar is greater than s square, this insists this is a binomial distribution, because we know for binomial distributions np, for mean is np and variance is npq. Okay, and since q lies between 0 to 1, because q equal to 1 minus p, this is again a probability, so expectation of x should be greater than variance of x. So another, this is the another reason to use binomial distribution. So when, first of all, if your n is small, that is 10 to 13 or 15, and p is not very small, then you can just look at the data set. First you check that whether it is a, first it is necessary, whatever n and p, first necessary thing is you should check whether it is a Bernoulli trap or not, because all the distributions, that is most of the distribution, that is binomial, geometric, negative binomial, Poiso, all are under Bernoulli trials. Okay, so first you need to check whether it is a Bernoulli trials or not. So that is first you check the trials are independent or not, uh, whether the success probability fixed or not. Third thing is, there are two possible outcomes, that is success and failure. First you need to check this criteria: trials are independent or not. There are two outcome of each trial, that is success and failure. And third thing is, you need to check, that is, the probability of success should be constant. Then you find out your number of trials, that is n, whether n is finite or not. Finite means here n is less than 30 or not. If n is less than 30, even if n is, I think it is some authors suggest that n should be less than 20 for binomial distribution, and p is not small. You need to check these two things, then find expectation of x and variance of x. Uh, that means, sorry, you need to compute sample mean and sample variance. If your sample mean is greater than sample variance, this thing is suggests that this is, you can fit a binomial distribution. Otherwise, you your if your n is not finite, that means n is greater than 30, your p is very small but np is finite. In that case you can use, and sample mean in the approximately sample variance, in that case you can use Poisson distributions, and so on. Or if np greater than 10, n minus 1 p greater than 10, this thing suggests that you can approximate this distribution by normal distributions. Okay, so this is the procedure. So first, I discuss the binomial distribution. Next we discuss, when we discuss next class, when we discuss binomial, Poisson and uh, normal distribution, I should mention this thing. For this class, you just keep in mind one thing: first you check whether this is Bernoulli trials or not. Second thing, n is finite or not, that is n should be less than 30, and p is finite means n should be less than 30. Actually, it is infinite doesn't exist. Okay, infinite means which we cannot imagine. So it is better we restrict the, we use the thumb rule, that is n should be less than 30 and p is not very small. Okay, so first these two things we check. One more thing, suppose your n is lies between 20 to 30, but p is not, but you do not know the p. So in that case, it is better you compute sample mean and sample variance, and then you check if the sample mean is mm, strictly greater than sample variance. The strictly greater than means it is visible. Actually, I want to say that clearly suppose mean is 2.5 and sample variance is 1.5, that is considerable. But mean is 2.5 but sample variance is 2.49 or 2.3. So it is approximately these two things are same. So clearly greater than. So sample mean should be clearly greater than sample variance. In that case, you use binomial distribution for this data. Okay. So thank you. If you have any queries and question, please tell me. Otherwise, I end this stream. So we will meet again with a new topic, new fitting, that is Poiso and normal, in my next class. Okay. So please stay with us and thank you for watching this video. So please tell me, have you any queries and question? If you have any queries, please tell me. Thank you. So have you any question? Otherwise, I end this stream. Okay. Thank you, Shah. Thank you, Shumon.